Hello, everybody. Thanks for tuning in. Today I'm going to talk a little bit about earthquake hazards and about warning systems. The key message or the narrative behind what I'm going to talk about today is to distinguish between the underlying process, in this case a storm, a supercell, and the hazards that result from that underlying process. In this case, rain, hail, or a tornado being spawned over here. Of course, in earthquakes, the underlying process is the fault, rupturing, and the resulting hazards is either shaking or a tsunami. Now, traditionally, unless you have dense geophysical networks, it is very difficult, if not impossible, to measure the hazard everywhere. And you can see that here. We have sensors at some discretized spacing, and seeing all the details of the shaking wave field that are occurring is impossible. As a result of that, the usual methods for earthquake early warning, they take a proxy approach where we try to infer something about the earthquake itself from these few sparse measurements, such as the hypocenter and the magnitude. And once we have a crude estimate of those parameters, we use those with some reduced physics approach to forecast what the shaking is going to be everywhere else. So that is what operates, for example, in the US today. Now that works. And the reason it works is because, as most of you know, earthquakes are comprised of P waves that arrive first and are of smaller amplitude, and S waves, which arrive later and bring the destruction. These are the ones that bring the energy of the earthquake to population centers. Now, because these arrive first, what we try to do is find features in these P waves that are diagnostic of the intensity of shaking that's coming with the S waves later. And that is quite trivial to do, and that's why earthquake early warning systems have been around for a long time. And the basic observation is that magnitude 5 earthquakes or smaller events have smaller P waves, and as you go to magnitude 6 and magnitude 7, you get bigger and bigger P waves. And the other observation is that the amplitude of the P waves is itself related to the amplitude of the S waves. So if we can measure these P waves and say something about the earthquake, then we can also forecast the intensity of the S waves that's coming down the line. And indeed, what you do is, once you measure all those P waves, before the earthquake starts, before your large event that you're worried about begins, you measure those P waves, stick them on a plot like this one, and you will find almost always a very nice log linear relationship between the earthquake magnitude and the amplitude of the P waves, whereas you go to larger and larger events, you get larger and larger P waves. And that's it. You have the basic recipe for an earthquake early warning system. An earthquake occurs, you measure the P waves, and from those P waves you back out the magnitude. Once you have that magnitude, you combine that with the distance from any given point of interest, for example, that of a city or a critical facility. If you know that distance from the earthquake, and you know the magnitude of the earthquake, and you also know a little bit about the local geology, whether you're on soft rock or hard rock, what you can do is, with those 3 bits of information, you can create an estimate of the shaking intensity. And you can make a map like this, which many of you are probably quite familiar with. This is called a shake map, where the colors represent how strong we think the shaking is going to be. Now, does this work? It does. And that's the reason why, starting this year, warnings from the Shake Alert system, the USGS Shake Alert system, are now being issued across the west coast of the United States. However, there's a challenge. If you were paying attention when I was discussing this earthquake early warning in one slide, you would have noticed that for the biggest earthquakes over here, the P waves actually seem to have an amplitude that is smaller than what you would expect from this log linear relationship. This is a well-known phenomenon called magnitude saturation. And what it means is that it's actually difficult to say that a magnitude 8.5 or a magnitude 9 is actually a magnitude 9. We frequently struggle with this. And indeed, we saw that during the 2011 magnitude 9 earthquake in Tohoku-oki in Japan. Here are the magnitude estimates, the different magnitude estimates from the real-time earthquake early warning system in Japan, which saturated, never exceeded about magnitude 8 or 8.1, when the real magnitude of the earthquake was just over magnitude 9. Now, this isn't unique to the Japanese system. Any system that relies on P waves, like this one, will see this. And if a magnitude 9 earthquake were to occur in the Cascadia subduction zone now today, we would also see this magnitude saturation effect. And of course, that's a problem, because if what we're interested in is forecasting shaking intensity, if we don't know how big the earthquake truly is, then our estimates of how intensely people and facilities will experience the shaking, they're going to be way off as well. So what do we do? One potential solution, and one that I personally favor quite a bit, is to use a different kind of measurement to measure crustal deformation using global navigation satellite systems, GNSS, which you might know as GPS. GPS is one of the constellations of GNSS. This is what a GPS or GNSS station looks like these days, a very fancy and expensive antenna measuring time of flight to all the satellites and being telemetred back to a data center. Turns out that during the 2011 earthquake in Japan, we had crustal deformation measurements. They weren't running in real time, but this is what the crustal deformation pattern looks like. And you can see that a 300 or 400 chunk of the coast of Honshu moved a meter or more towards the ocean. You don't need to be a particularly good seismologist to figure out that if that much motion happened over that extent of coast, then a big earthquake has just occurred. So we want to leverage that. Now, of course, there are a couple of challenges. One is that that pattern of deformation can be quite complex and quite rich, so you need an algorithm that is able to tease apart all those complexities. This is shown here for a simulated 8.7. I'll show the Cascadia subduction zone. The other challenge is that if you want to use things like modern data science and machine learning, which require a lot of events to train an algorithm, we just don't have enough of these large magnitude events. That's good. We don't want to live in a world where we just experience 10,000 magnitude 9s. But for training the algorithms, it's difficult. So our solution to this, or the approach we've taken, is to simulate all these large earthquakes by the tens of thousands and simulate all these crustal deformation patterns and use that to train machine learning algorithms. An important question is, well, how do you know that this is going to work or that you're actually doing a good job? The answer that we've proposed to this is to go somewhere where there have been at least a few large earthquakes in the past. So we're applying this machine learning approach to the Chilean subduction zone, shown here, this incredibly long subduction zone. Here you see a simulated magnitude 9.2. Chile also has a really nice network of currently operating GNSS stations, and they also have had 5 earthquakes, shown here by these beach ball symbols. 5 earthquakes that have occurred in modern instrumental times, for which GNSS has been recorded. In particular, this magnitude 8.8 Maule earthquake in central Chile. So we train our algorithm on simulations in Chile and then validate against other simulations, but also against this real recorded data. Here's a performance of the machine learning algorithm with scenarios, with simulations that were not used in training. They were left out. And where you want to be is along this one-to-one line between the actual magnitude of the simulation and the predicted magnitude from the algorithm itself. And the gray region is the plus or minus 0.3 magnitude unit region, which is a number traditionally used in earthquake early warning. You want to be inside that region to say that you're doing a good job. There are some outliers, and these are I'm happy to talk about those later. But by and large, I think we're doing a pretty good job with these left out events. But the real star of the show is the fact that with the real data, we're doing pretty well as well. So here are those 5 events, and what I'm showing you here are the machine learning magnitude predictions for those 5 events. For the real data, and especially for the magnitude 8.8 earthquake in Maule, the machine learning algorithm, by about 50 seconds after the start of the earthquake, is already predicting 8.5, and by 60 seconds it's hitting 8.8 when the real final magnitude was 8.8. There's a little bit of an overshoot before the prediction comes back down, but by and large, this is phenomenal performance for such a large event, especially considering that this data did not go into the training. And we see similar performance for a magnitude 8.1, a magnitude 8.3. We overshoot a little too much for the 7.7, and we do quite well as well for the magnitude 7.6. So this is great. Now, it's great because in the west coast of the US, which is where we eventually aim to deploy this algorithm, we are swimming in real-time GNSS stations, both in the Pacific Northwest and in California. And other algorithms as well are being tested and deployed. But even though this is great news, we still haven't solved the problem of forecasting the shaking itself, which, as I've told you, is the ultimate goal that we're after. So actually getting this shake map got a little bit easier because we figured out magnitude saturation by including GNSS, but getting all the minute details of the shaking pattern are still very difficult, even with GNSS. So we're still chasing this model of being able to forecast the hazard everywhere surrounding this underlying process, which is the earthquake itself. So why not take the same approach? Here's an animation of the 1989 magnitude 6.9 earthquake in Loma Prieta. This is the World Series earthquake of '89. And what you're seeing here is the shaking wave field developing as the earthquake grows. So if we have a network of stations, shown here by these green squares, perhaps we can do the same. What if we simply train an algorithm to say, based on the pattern of shaking that I see now, forecast into the future what you think the shaking is going to be 10 seconds or 20 seconds forwards in time, using the same strategy. Well, we've started doing that. And what I'm showing you here are our first very modest steps to that goal. What you're looking at is 6,000 earthquakes in the LA region, dating back to 2000. And this is the network of seismic stations that have recorded these 6,000 events. So what we're doing is training an algorithm that only sees the first 1 or 2 seconds of this P wave, and we're asking it to predict what the shaking intensity is going to be when the S waves arrive. And here's the performance. On the left is what a traditional earthquake algorithm would do in terms of the actual observed shaking intensity versus the predicted shaking intensity by the algorithm. This is what ShakeAlert would do today. This is the one-to-one line in yellow, and then in blue and in green, the plus or minus 0.5 and 1 magnitude unit, intensity unit error. There's a lot of scatter here. You're on the right trend, but there's a lot of scatter because shaking is difficult to predict. Meanwhile, the machine learning algorithm has a very tight distribution, almost all of it contained between the plus or minus 1 intensity unit contour. So this is great because we no longer, in this process, we're simply taking shaking to predict shaking. We're not actually going through that proxy approach of learning about the earthquake, its magnitude, its location, to predict the hazard. So this is a good improvement. But once more, if you were paying attention, you would have noticed that all my data is for low intensity shaking, shown here on the left. At the high intensities of shaking at MMI 5, 6, and 7, which is where damage begins to occur, we're still very much data limited. But since we already know how to play this game, let's do the same thing, and that's what we're doing now. Take simulations, the same simulations that we used to predict the crustal deformation, these arrows, but actually use it to predict the shaking intensity. That's what's shown in these squares. These squares show the intensity of shaking in units of G for this same simulation. So we can use that to train machine learning algorithms, but we have many more difficulties. Simulating ground shaking realistically is tougher because we need to capture the 3D geology really, really well. For example, whether we have a sedimentary basin, like the Willamette Basin here, or whether we have a volcanic arc, is going to affect the intensity of shaking predictions quite a lot. It's numerically very intensive. It takes a lot longer to model shaking than it does to model crustal deformation, but we're working on it and we're making good progress. So I foresee a future, 5-10 years from now, where we're cranking out tens of thousands of these simulations and we're using them to train machine learning algorithms. And before I finish and before I conclude, I'll say that the same strategy will work for tsunami early warning. Here's the crustal deformation from a magnitude 9.2, and here's the tsunami from that same magnitude 9.2. Running these tsunami models is now computationally very, very efficient, and they have all the right physics, the right bathymetry, the right topography, the right everything. So we're also going to be in a future, in the not too distant future, we're going to be in a place where as the crustal deformation patterns unfold, we're immediately going to be making predictions of what we think the amplitude of the tsunami is everywhere along the coastline. So I'll finish here. Traditional earthquake and tsunami warning methods have always taken this proxy approach of, from a few measurements, do your best to characterize the underlying event, the earthquake, figure out its magnitude and its location, and then from that crude estimate forecast using also reduced physics what the hazard is going to be everywhere else. And this works okay. This is what's implemented in the US today, but it can be imprecise and it's particularly challenging for the largest earthquakes. Now, because there are now very dense geophysical networks and because we're getting really good at simulating thousands of these large earthquakes, we can now realistically think of using things like machine learning to make all of that a lot better. Now, I don't mean to say that all we need to do is observe and model and we're going to be doing great. Basic science advances are still fundamental because the simulations are only good because they're rooted in a strong physical understanding of rupture physics. That science needs to be correct for the models to make sense and for the machine learning algorithms to make sense. So we still need to make a lot of progress there. So I'll finish there, and hopefully I'll see you later and maybe take some questions. Thank you.